to x of the y component, which in this case is I times f. I pulled the I out, all right? And on the other hand, minus partial derivative of the x component, the coefficient of dx, the p, in the usual language of pq vector fields. So this is q dx, partial q partial x minus partial p partial y in the usual, Stewart nomenclature of Green's theorem. And why is that 0? The Cauchy-Riemann equations, right? That's 0. So that means that the integral around the triangle is 0, which means that the sum of the integrals along the legs of the triangle must be 0. But these are special things. You see, notice I put a minus here because if I go counterclockwise around that triangle, counterclockwise, right? I have to think about this. So that's like this way, that, and that. So this one here, from x naught plus iy to a, you see, it naturally would be from x naught plus iy to a. Do you see that? But I put a minus here because I wanted to flip it. The reason I want to flip it is my h of z is defined by the integral from a to stuff. So this is an h of x naught plus iy. This is an h of z naught. So I solve, I get h of x naught comma y minus h of x naught y naught equals to this guy. But this guy, when you parameterize that line segment, which is a what? It is a vertical line segment, which means that the dz is actually I dt here. So since dz is I dt, I get the I out here, I get the dt, I have f of x naught comma t from y naught to y. And then if you differentiate this with respect to y holding x fixed, or if you take, however you want to see it, the fundamental theorem of calculus part 1 then implies that the partial derivative of h with respect to y, notice x naught's fixed here, see that? So if I differentiate this equation with respect to y, this will become the partial derivative of h with respect to y at x naught y naught. And this literally gives me f of x naught y naught. That's half of what I need. And then what do? You use the other triangle. You use the other triangle. So the other triangle, and I won't belabor it, but you can work through the other triangle, and then you get that partial h partial x is equal to f of x naught y naught. So let's put it together. We have that f of x naught y naught is on the one hand the partial derivative of h with respect to x. On the other hand, it's 1 over I times partial h partial y. Well, that means that partial h partial y is equal to I times partial h partial x. What does that mean? That means that h satisfies the Cauchy-Riemann equations, therefore h is complex differentiable, right? But the point z naught was arbitrary, hence we've shown that dh dz is equal to hx, which by the way is equal to f on the given star-shaped domain. And then finally, set my silly h equal to big F, and then you've got the statement of the theorem. So this is actually how we build the potential function from a given complex function. We do this line integral like this. So, and this, by the way, guys, this gives us a way to define the logarithm in terms of an integral. Yeah, Jeff.
Where was the 1 over I partial h partial y?
Where is the what?
The 1 over I partial h partial y. Was that in the first part?
That was in the first part because at the end of the first calculation we had an I. So I ended up with partial f. See, I got, look at the, whoa, that's kind of cool, right? I did not leave the cursor there, but look what it's doing. God is sovereign. See here, so partial h partial y is divided by I. The reason I did that was because I can compare both of them to the value of the function at the point, which then gives me the Cauchy-Riemann equation for h, which shows me that since h is, now admittedly I need the continuous differentiability of h, right? So there's some finer points of analysis that my proof is missing perhaps, but anyway, so applying this idea, check this out. So f of z is equal to 1 over z. It's holomorphic on the star-shaped slit complex plane. Do you guys, Let me draw the picture for what this example is doing, because I think I have a homework question which is like this. So I want you to understand what I've done here, so the homework question is like not so challenging. So what I'm doing is I am, let's see here. So first of all, if I define log z like I do there, then it's automatically true that ddz of log z is equal to 1 over z for z in the slit complex plane. So here's the slit complex plane. I'm integrating from 1, right? And I guess maybe my point could be like this. So, oops, try that again. All right, so here it is. This is my z. Now, I've made z, the modulus of z, larger than 1. So what I do to get over here is I first go out to modulus of z on this line segment, and then I track like that along this. Z equals to modulus of z e to the it, where for mine 0 is less than or equal to t is less than or equal to, they say, theta naught, where I'm assuming that z is modulus of z e to the I theta naught. And so since the integral is independent of the path I take here, as it turns out, I can do the integral however I want. But this is super nice because integrating along this is a nice calculation. Integrating along that is a nice calculation. And when I do that, what happens? Well, I have, for the real part, I just have integral of dx, over x from 1 to modulus of z naught. It's okay, I got it. It's all good.
It's all good.
It's all good, man. Yeah. It took me a while to hear that. Saul Goodman. Anyway. So, this is the integral along the real axis. Here I'm assuming that the modulus of z is larger than 1 for the sake of computation. If the modulus of z was less than 1, then I'd have to reverse the direction of the integration, and it would bring a minus that compensated. And it would still end up working out to this. Like whether or not the modulus of z is less than 1 or greater than 1, it's still going to work out to natural log of the modulus of the thing we're looking at, plus I times the argument. But that is heavily dependent on choosing the angle appropriately to the slit complex plane, right? You can see, if you study this integral, that it's going to generate angles in the imaginary part that are between minus pi and pi by construction. So this integral is a way to define the principal logarithm by an integral, as opposed to a formula. Now, of course, if you do this, it still begs the question, well, how do you know that this function, so defined, right, is actually the inverse to the exponential? But I suppose after you calculate this formula, it's easy enough to plug it into the exponential and see that it's an inverse, right? And there's probably another way to see it that's more elegant than that, but I would point out, I thought about this for a little bit. I think we could define, I'm about 95% sure this example is right, but I think we can define log sub alpha of z by the integral from e to the minus I alpha to z. So this is, think about this, for log alpha, we delete the ray at angle alpha, so like multiples of t e to the I alpha. So this minus e to the minus I alpha, it's the analog of 1 in my previous example. It's like on the opposite side of the origin. It's in the place where the C alpha slit plane, that's part of this. This is a star center for C upper alpha is what I'm trying to say, okay? This is a star center for C upper alpha. And I'm pretty sure that this is how to do it. Now, this is weird. I had to think about this for a little bit, but in order for us to get a range of angles see, pretty much this integral, if you think about this integral, it's the same as the one we just worked through. It's going to generate values between minus pi and pi. So if you want the angles to actually go from, say, alpha to alpha plus 2 pi, I have to shift the imaginary part by this sort of ad hoc correction term. And so what this does is if you put in, if this thing works out to minus pi, this goes to alpha. And if this thing goes to pi, this goes to alpha plus 2 pi. Well, it goes to, yeah, I mean, see, this would go to alpha plus 2 pi, right? The imaginary part of this would be alpha plus 2 pi if this integral works out to pi. So anyway, I'm pretty sure this formula is an integral definition of our log sub alpha if you care. If you don't care, that's cool. So this brings us to Cauchy's theorem. Cauchy's theorem says the following. It says if f of z is holomorphic and continuously differentiable on D, and if it extends continuously to the boundary of D, then the integral of the complex function is 0. So here we have to understand that the boundary of D is the oriented boundary of D, where the inner boundaries are oriented clockwise, whereas the outer boundaries are oriented counterclockwise. At this point, I'm going to put this away and explain to you what I mean by that. We'll look at the proof of Cauchy's theorem starting next time, okay, guys? But I need to explain what I mean by about that. I need to draw you a picture. Because I don't know if you guys, when you did calculus, when you did calculus 3, you should have done Green's theorem with a hole, right? We start by doing Green's theorem without holes, but at some point or another, you should do Green's theorem on like Swiss cheese. All right. So like that could be the region, and those are deleted. So the Green's theorem, it applies on a space which is it has to be bounded. It has to be bounded, and it has to be piecewise smooth boundary. Okay. So piecewise smooth boundary is necessary so that you can break it up. You can integrate along the edge by breaking it up into a finite number of sums where each piece has like a parameterization. So we can go back to our parametric definition of the integral, right? But if this is my domain D, right? Then the boundary of D, it should be made so that if you can imagine yourself like an ant or something walking along the boundary, which side of which if you're walking in the positively oriented sense, should the surface be which side of your should be on your left or should be on your right? Left, right. Incorrect. Yeah.
50% chance.
So the answer is we want to do counterclockwise outside boundaries, and we want to clockwise inside boundaries. That's the way it works. So what that means is so like out here, like here, right? So that's opposite the direction of a clock. If you guys know what a clock is. You guys know what a clock is. You know what time it is, right? So clockwise in here, like this, right? This becomes important because we're going to apply Green's theorem on regions with holes in order to derive interesting theorems next class. All right? Something more important than my class, Ernesto?
An appointment?
An appointment?
Sorry.
An advising appointment?
No, it's a car place.
A car place? Okay, yeah. Those people are definitely more important, yes. I thought maybe it was like the geometry test or something, but, well.
Oh, we do that.
Do you have that? Are you ready?
Thursday. I'll be ready.
Oh, Thursday. Oh, okay. Well, that's cool. So, listen, when we write stuff like this for Green's theorem, when you write integral over the boundary of D of p dx plus q dy equals to the double integral over D of, like qx minus py, this is Green's theorem, right? You should understand that this theorem is true on regions like this. You might have spent most of your time in Calculus 3 looking at regions without holes, but it is in fact true for regions with holes, because you can always take a region that has holes and cut it up into regions that don't have holes. Like this one, what you do, I should have chose something, let me choose something simpler. So if my region was like this with one hole, right? I can make this into two regions without a hole by just simply doing this and this. See, I go like that, and then I go like this. Let me think about that. Other way around. Like that. I do these cross cuts. Like that, and down here like this. So I just basically cut it, and if I do that, then the natural, you can take the region with a hole, cut it to two regions without holes, and then when you add up the integral around the boundary of the cut pieces, the cross cuts cancel, and you obtain this theorem. This is what happens. But this should have been done in Calculus 3. I don't want to really reinvent the wheel here, so I'm just telling you, reminding you this. If you've never seen that before, you should talk to me in office hours or something. I can explain it more slowly and show you where it's in the Calc 3 book, stuff like that. Anyway, I should stop. I think I'm now to the point when the last student entered the class at the start of class, so taking my pound of, yep, oop, a minute over.